All right, so we're going to take the derivative of it. There's a lot of ways to take the derivative of it. This is going to be a longer video. So first, we're going to take the derivative like we already know how. We can already take the derivative of this. We're capable. We know all the rules. We just first have to make it into a better form. So let's FOIL. So let's do that times that, 15x, that times that, 12x squared, this times this, negative 10x squared, and this times this, negative 8x cubed. And then let's just combine like terms because we can. So we'll combine these here. So we'll go 15x plus 2x squared minus 24x. No. 8x cubed. I don't know what I was thinking there. So that's h of x. And now, this is important to remember. People in calc get confused about this all the time. That we didn't take the derivative yet. We just did some math, so now we're able to take the derivative. But now it's easy to take the derivative. H prime of x is 15 plus power to the front, decrease power by 1, 4x, power to the front, decrease power by 1. So that's the derivative. That's the answer. We could be done with this problem if we wanted to. But I don't want to be done with this problem. I want to solve it a different way. Because that's the beauty of calculus. That's always what I loved about calculus, is that we can do this problem in a totally different way, in multiple totally different ways, and get the exact same answer, because that's how math works. So let's do it in a totally different way. But to do it in a totally different way, we need to use a new rule that we don't know yet. Or at least to do it in the totally different way that I want to do it in. So let's remember what our answer is. And we need to derive a new rule. That's what we're going to do. So first off, I want to do it visually because I think that's more interesting. So this is just ripped off straight from 3 Blue, 1 Brown, but I doubt that he was the first one to come up with the idea either. So I'm going to show it to you as well. So here's the idea. What do we have here? We have an h of x. We have a function. But what it's really made up of here is two different functions, right? A function there, f of x, times a function here, g of x. And so maybe we want to define these for ourselves. So we're saying that f of x is equal to that first function, the first thing, 3x minus 2x squared. And the second function is equal to the second thing, 5 plus 4x. And we want to take the derivative of those two functions multiplied together. So to do that, we can't just take the derivatives of both of them. It just doesn't work like that. That's why we have what's called the product rule. And that's what we're going to derive right now. So just to be clear, we're going to derive it. This is not the process you do every time you use the product rule. We're going to start from bare bones, and we're going to figure out why the product rule works. And again, this is one of those things you don't have to do every time. It's just really nice to see it once. Honestly, I think last night, for the very first time, I did it for the first time. I'm not sure I've ever proven the product rule before, but it's really cool how you can do it. So first off, let's start visually. So what do we have? We have f of x times g of x that we're trying to take the derivative of. So we can think about that as area, right? Because it's multiplication. So we'll call this side f of x and this side g of x. So then like the area of this square is the h of x. And then we're going to do this. This is a little strange, but here's what it is. So we're going to think about, because what the derivative is a little bit of change. We change things just a little bit. We change x just a little bit. So we're going to draw this little bit here. That's going to be like, we're going to call it, that's our change in f of x. That's how much f of x changes by. And then we're going to add on this little bit here. That's our change in g of x. If you know physics, you know this is like delta. That's just change. So we're saying we have our change in f of x and our change in g of x. But then when we do that, look at how that changes. Whoa. This one. Shouldn't have had anything modified on my iPhone. What? That's weird. This one. So look at how the area changes. So when the f of x changes by a little bit and the g of x changes by a little bit, the area will change by a little bit. But then let's be specific about how much did that area change by? What is the area of this box right here? Well, what are its side lengths? Well, its side lengths are f of x, and then its other side length is the change in g of x. So that area is f of x times the change in g of x. And then this area down here, similarly, that's g of x there, that side length. So this area is g of x times the change in f of x. And then this little bit right here, you see what those side lengths are? That's the change in f of x. No, that's the change in g of x, that side. The change in g of x, and this is the change in f of x. So then you do this. You go, so what then is the change in the area? Well, the change in the area, that's just this part right here. That's just adding up everything we added together. And since h is the area, that's like saying that the change in area, let's do that. The change in area, the change in h of x is equal to the change in f of x times g of x plus the change in g of x times f of x. So see, that's just this section here and this section here, plus that little square down there, or that little rectangle down there, the change in g of x times the change in f of x. So that's a beautiful formula. Now the last connection that we have is that we're talking about the derivative. So these changes are really just like little tiny changes that don't actually matter. Or more specifically, like the derivative. So now we can rewrite this thinking of h prime of x, because we're talking about the derivatives, and that's just how you write the derivative, is equal to f prime of x times g of x. We're basically just changing all the deltas with like primes, plus g prime of x times f of x. And then the whole deal with these is when we talk about these being infinitely small. Look at how like this here, it's all, and then it's all comparison. So this is something infinitely small times something infinitely small. That's like infinitely small squared. Versus this is just like infinitely small times not infinitely small. So what is bigger? And what we actually find is that this here, since it has a whole nother infinitely small, it's so small it doesn't matter. So this part here doesn't actually get included when we start talking about the derivatives. We just have it right there. And actually, if you know the product rule, you'll recognize that that is the product rule right there. You can just look at it by adding together the two areas of those rectangles. That's visually where the product rule comes from. And let's go ahead and use the product rule now. We're still going to derive it another way, but let's use it first and make sure we get that same answer there. So what are we going to do then? This is like kind of a bigger process, because we got to take the derivative of f of x, the derivative of the first function. So we have to use power rule there. So that's going to be 3 minus 4x. And then we have to multiply that by g of x, the second function, 5 plus 4x. So that's the derivative of the first part times the second function. And then we add the derivative of the second function. So the derivative of the second function is just 4 times the first function 3x minus 2x squared. And that's the derivative. From here, you probably want to simplify, which we will. So we're going to FOIL here, practice our Algebra 2 skills a little bit, or Algebra 1 skills, really. 3 times 5 is 15. 3 times 4 is 12x. Negative 4x times 5 minus 20x. Negative 4x times 4x. Negative 16x squared. And then distribute the 4. So plus 12x minus 8x squared. Lastly, we're just going to combine like terms. So we have here 12 plus 12 is 24 minus 20. So we have 4x. We still have that 15 in the middle. So 15 plus 4x, or 15 in the beginning. And then we have negative 16x squared minus 8x squared. So minus 24x squared. That should be the derivative of h by using the product rule. And let's check, does that match our answer up here? 15 plus 4x minus 24x squared. Beautiful stuff. Beautiful stuff. Beautiful stuff. So we've got one last thing we've got to do. We've got to derive the product rule for real, like analytically. So I think we're going to add a page to do that. So here's the deal. What is the very base definition of the derivative? We still have to know that. I know it's chapter 2, but we still have to know that. And I know we're learning all these rules to avoid it. But what it is really is, remember that it's just the slope between 2 points when x is equal to x plus h and when x is equal to x. So we have f of x plus h minus f of x over, and then it's just this, but it's x plus h minus x because it's just the slope. But it's nice to simplify it to just be h. Because at the end of the day, remember, what is the derivative? The derivative is it's just like the slope between 2 points. But then look how as we make h equal to 0, those points get closer and closer and closer to each other. And so it just becomes the slope of the tangent line, which is really what the derivative is. So we definitely want to keep that in mind. So what are we actually going to do here? Well, in this case, what is our function? Well, yeah, let's copy down our function. Or let's just copy this and bring it down here. Well, we don't want all the words, but that's fine. So we're going to picture it. It's actually, no, I'm sorry. We don't want the function yet. Because all we're dealing with is h of x equals f of x times g of x. And so we're trying to take the derivative of h of x. So the deal is, it's like if we start applying this formula, what we're doing then is the limit as h approaches 0 of, you see, it's f of x plus h, or in this case, h of x plus h. So that means we're plugging in x plus h everywhere that x would be. So we're going to have f of x plus h times g of x plus h. And then minus, see, just like h of x, so the whole function, just the normal function, f of x times g of x. And then all of that is divided by h. So see how we just, I feel like I need to rewrite this because none of those letters get confusing. But remember, they're just stand-ins. They're just variables. They can be anything. Oh, but then that's horrible with that. Yeah, that doesn't work with that then. But yeah, so see, this is our h function. That's h of x plus h. That's the h function with x plus h instead of x. And then minus h of x. So that's this part right here. That's just the normal h function. And then all of that divided by h. Remember, that h is not related to this h up here. So now what? Now's honestly the kind of like the super, super insightful step that I stared at this. I tried to get it on my own. I honestly had to look in the textbook to see what you have to do next because it's pretty wacky. So here's what we're going to do. I'm just going to copy and paste this because we're going to take this And we're going to do something wacky in the middle. So let's actually move this out further. Because watch what we're going to do. This is so wild. So let me get a distinct color. Let me get the nice pink. So here's what we're going to do. We're just going to randomly subtract f of x times g of x plus h. We're just going to do it. Why are we going to do it? Why are we going to subtract that specific thing? We'll see in a minute. But obviously, you can't just subtract a random thing. So we have to, in turn, add that random thing. Weird, right? So notice we didn't change it because we just subtracted something and then immediately added it. So they just cancel each other out if we wanted them to. We just don't want them to, because watch what we're going to do next. Next, you want to picture how we have these two parts now. We have we're going to have, say we have this part here and this part here. And just to be clear, let me extend this bar out because that whole thing is over h. But now let's do a couple things and let's do it in one step. So we're going to heart this fraction, meaning we're going to separate this into that fraction and that fraction. So they both have the same denominator because that's how separating fraction works. And while we do that, we're also going to factor out what we can. So look at how in the first part, both of them have a g of x plus h. So we can factor out g of x plus h from those first two terms. And what are we left with when we do that? We're left with f of x plus h minus f of x. And we're going to have that. Actually, we're not going to have it all over h. We're going to have just this part over h. Because remember, when you have a whole fraction and they're just multiplied, it doesn't need to be at the top. That's just like that over 1. So recognize that that's the same thing. As if that were just one fraction, we can just pull this out to the front if we wanted to. And then we're going to do a similar thing for the next part. So we're going to have plus, let's see, what can we factor out here? Here we can factor out an f of x. And what are we left with when we do that? G of x plus h minus g of x over h. And now here's the thing. Remember this limit. This limit is still there. So since there's two things added together, we can actually separate it into these two different limits. And then here's what you have to recognize now. Look at this. Look at this part that we have right here. And look at this definition of the limit that we started with. What we have right there, when we apply this limit as h approaches to 0 to it, is the derivative of f. Because that's just what this is equal to up here. That's equal to the derivative of f. So this part right here, when we go to plug in h equals 0, that becomes just the derivative of f. And then what happens here when we plug in h equals 0? Well, x plus 0 is still x, so that's just the normal g of x function. And then the same thing's going to happen over here. Look how here we have the same thing, but just with g instead of f. So instead of that being the derivative of f, that's the derivative of g. That's g prime of x times, right here, f of x. And those are added together. And look at that. That is the product rule when you derive it from the limit definition. That's beautiful. So the key thing, the key crazy insight to me was this add and subtract thing. That's what was so cool. And when you do the quotient rule, the exact same thing happens actually. But we will get that to the next video because we've done a lot for this one. We found this derivative in two different ways and proved the product rule. Proved the product rule really one way and saw a nice visual for it another way. That was a good stuff.